So by just naively having 10,000 threads incrementing 10 array elements, we got the wrong answer. One solution might be to sprinkle barriers throughout the code that I just showed you. But another solution is something called atomic memory operations. Atomic memory operations, or atomics for short, are special instructions that the GPU implements specifically for this problem. And there's a bunch of atomics. You can get the list in the programming guide, but some of the examples that you might use are atomic add, atomic min, atomic XOR, and so forth. A particularly interesting one is called atomic CAS, which stands for compare and swap. Let's look at how these work. Okay, so here's our code again. And in this time, instead of calling increment naive, let's call a new function, increment atomic. This kernel is almost exactly the same. Every thread computes what thread it is, and then it mods that by the size of the array to figure out where it's going to write. But the difference is that whereas before, we were just doing a standard C operation, g sub I equals g sub I plus 1, which has one read, a modify, and a write. Here we're going to use the atomic add operation. So this is a CUDA, this atomic add function is a CUDA built-in that's going to take a pointer, which should be to somewhere in device memory, shared or global memory, and an amount to add, a value to add. Okay, so this has the same effect. Every thread's going to go and add 1 to the value at g sub I, but the difference is that this is using special hardware that the GPU has built in to perform atomic operations. So now we're guaranteed that only one thread at a time can do this read, modify, write operation. Okay, so now we'll scroll down, change our code, call increment atomic. That's the only change we'll make. Compile the code again and run it. So this looks more like it. Now we're writing 1,000,000 total threads and 1,000 blocks, writing into 10 array elements. And this time, as we expect, every array element contains the number 100,000 when all is done. Okay, so the atomic operation prevented these collisions where multiple threads were trying to read and write from the same memory location at the same time, and instead serialized them, making sure that only one thread at a time has access during the course of that read, modify, write, that add operation, and we get the right result. Notice it took longer. Before it took about 3 milliseconds, now we're taking about 3.7 milliseconds. So atomic operations come with a cost, and that's something I'm going to go into. Let's run this a few more times to make sure that we get the same result. That time it took about 4 milliseconds, closer to 4 again, down around 3, and so forth.